on Shanna Nights. I'm really happy, dear Shanna, that you are here. She's the Director of Technology Collaborations from Ballard Power Systems. And as you can see here, her screen, she's talking now to us. It's the last presentation before we have a short and lively panel discussion. She's talking about fuel cell catalysts for zero emission heavy duty application. I think every one of you knows Ballard, but I'm pretty sure Shanna gives you some words about her company. Dear Shanna, it's your turn.
Thank you, Silke. And thank you to the organizers. I'm very happy to be here or virtually be here. So I'll just, as Silke mentioned, I'll talk a little bit about fuel cells, about Ballard, and about fuel cell catalysts. So this is my outline. So I'll start with introducing Ballard, and in case you don't know or just give you more information about it, why we need hydrogen for global decarbonization. I'll go into some specific applications, which is the fuel cell buses and trucks and what the value proposition is there for fuel cells. And then I'll try and link the fuel cell catalyst requirements. We've heard about catalysts today and materials, and I'll try and link those together with the applications in use. So this slide just shows some numbers associated with Ballard, how we characterize the company a bit. We've been around for more than 40 years. We have 900 employees. We have a lot of intellectual property. We're a publicly listed company. In terms of products and vehicles that are using Ballard fuel cells, there's more than 1,000 transit buses, more than 2,200 trucks. We're working on 4 train projects, 6 ships projects, and there are more than 12,000 forklifts in operation using Ballard fuel cells. We have programs for high power density stack development. We've delivered more than 670 megawatts of fuel cell products and produced more than 5.5 million MEAs. Vehicles powered by Ballard fuel cells have gone more than 50 million kilometers in operation. And we have fuel cell stacks that have run for more than 35,000 hours in the London buses. So Ballard produces fuel cells. That's our business, and we work in PEM fuel cells. And this slide represents some of our markets and solutions we're working on today. So around clean mobility, we produce fuel cells for heavy-duty vehicles and rail, for marine vessels, materials handling, and light-duty vehicles. And for those, we produce fuel cell power modules and fuel cell stacks. For stationary systems, we have fuel cells for distributed power generation and backup power solutions such as critical communications infrastructure. And for those, we produce fuel cell power systems. We also do technology solutions, which is working with customers for their own fuel cell development programs, and we provide a number of solutions services to them. So why is hydrogen important for the future? So we've all heard today, we've been introduced by a few speakers about the need for global decarbonization. We all know that. We also need to decarbonize to fight climate change, as well as air pollution. That's an issue in many cities around the world, and hydrogen is part of the solution to do that. Hydrogen is a flexible energy carrier and fuel. It's clean, used in cars, trucks, buses, trains, and ships. It can also be used in industries such as mentioned for the different chemical industries, as well as for critical infrastructure. So hydrogen is really key for some of those sectors in the energy industry that are difficult to fix, and governments are recognizing that. I'm just going to pause. Maybe Silke, I think maybe you need to mute. I'm hearing I'm hearing some typing. Thanks.
Shanna, we can hear some noise. Is there anything that you can change, perhaps?
It's not coming from me. I'm hearing it as well. On the computer.
Okay. So is any one of
I apologize.
those?
I believe it was me. I'm muted now.
Okay, perfect. Thank you.
Thanks. Okay, so I'll keep going. So there's 18 countries, at least, and that number is growing, that have developed hydrogen roadmaps because they see the importance of hydrogen to future economies. Those countries represent 70% of global GDP. So these are the leading countries. The Hydrogen Council is a group of CEOs of major multinational companies in the energy, transport, and different industries that believe hydrogen is critical. And they formed this council in 2017, and there are now 92 members. And they are really promoting the use of hydrogen and want to see the industry established strongly. So the Hydrogen Council has a vision for 2030 of more than 10 million fuel cell cars on the road, 500,000 fuel cell buses and trucks, and hundreds of trains and vessels. And our industry will deliver this vision through economical and low carbon hydrogen, green hydrogen, and by reducing cost of fuel cells.
Explain, what are we shipping?
So hydrogen is most competitive in the heavy duty motive applications. It will have, use in many different applications. I myself drive a Toyota Mirai car, which is a, wonderful experience. And we see a lot of fueling stations in Vancouver where I live. But we also see that the heavy duty is where we're going to have the highest value proposition. So buses and coaches, trucks, trains, and marine vessels are the earliest applications. And fuel cell technology is really needed to decarbonize those sectors. So fuel cells work with batteries. It's not, we're not competing with batteries, but we work together. But there are areas where batteries alone are not sufficient. And so that's where combining a fuel cell with a battery in an electric vehicle is really the best solution. And only fuel cell based vehicles can directly replace diesel route for route. So they provide the same type of performance regardless of the weather. So you don't have a derate, say for example, due to cold conditions, provide the same type of range and payload. And the refueling time is similar to a diesel as well. They're very adaptable. They're, as I mentioned, they're hybridized with fuel cells and batteries, and you can design your system for many different drive cycles. They're very scalable. You can have many different sizes, and they can be optimized for the vehicle you need. The high energy density, I think we've heard about that already today as well, enables longer routes and heavier payloads and hotel loads than a battery electric vehicle would do. The infrastructure is also very scalable. It's easy to, it's the same as we're used to now with liquid fuels. You just have larger tanks and you can fuel more vehicles. You don't have to add more charging stations, for example. Hydrogen is already widely available today, but the expansion of renewable hydrogen is growing, and advancements in the hydrogen conversion will give us more renewable options, which of course are very important for decarbonization. And most importantly, the costs are trending down. We've seen significant reductions, and based on a number of studies, but we're expecting further significant cost reductions. So in terms of, if you see the blue curve, we can see that the fuel cell vehicle cost is soon will beat that of battery electric vehicles, and will also be cheaper than diesel internal combustion vehicles in the relatively short term. So we expect the fuel cell system cost to drop by 70%, and hydrogen distribution and refueling costs will drop by 40%. And this chart represents the total cost of ownership based on a study from McKinsey. So by 2030, we expect it to be cost competitive in a number of applications. This is data from E4Tech, which is a company that publishes annual reports about the status of the fuel cell industry and shows the amount of megawatts of fuel cell shipments every year. And as you can see, the fuel cell technology is significantly increasing every year and is accelerating. And this also is broken out by the type of fuel cell. We saw a nice slide earlier on the different types of fuel cells. And the PEM fuel cell is really dominating. That's the type of fuel cell that Ballard produces exclusively. And that's because of the temperature range makes it very suitable for mobility applications, and it uses atmospheric air. So this is the area that's the most commercialized type of fuel cell today, and it's expected to continue to grow. Looking at Ballard, we're a global company. We're headquartered in Vancouver, Canada, but we have operations in the US, in Denmark, and the rest of Europe, and a number in China as well. And we have manufacturing facilities, R&D facilities, and service facilities throughout the world. And we work with a number of different partners to deliver our fuel cell solutions. So very briefly on Europe, as we're operating in the Europe time zone right now, we have our European headquarters in Denmark, and that's also where the Ballard's Marine Center of Excellence and our Critical Communication Infrastructure Center of Excellence are located. And we have a manufacturing capacity of 60 megawatts per year. We have more than 80 employees in Europe dedicated to sales, market development, engineering, manufacturing, service, support, and training. And they service more than 60 heavy-duty vehicles in operation, are conducting 2 rail projects, developing fuel cells for rail, 6 marine projects, and support 380 backup power systems, which are in service. So now looking at buses, Ballard has been working in buses for a long time. I've been at Ballard for 25 years myself, and one of the first projects I worked on was some of our earliest buses in revenue service. And currently there are more than 1,000 buses that powered by Ballard. And we work with multiple different bus manufacturing companies in Europe, the US, and China. Our buses powered by Ballard fuel cells traveled more than 25 million kilometers in revenue service. And we've demonstrated more than 30,000 hours of fuel cell stack life. This map shows fuel cell buses worldwide, and the green numbers are all the fuel cell powered buses, and the blue are Ballard fuel cell powered buses. So the ones with Ballard fuel cells. And we see that it's really dominated by Asia at the moment. That's been a lot of rapid growth in the last couple of years, where they have more than 3,000 fuel cell buses. And then we see Europe also has quite a few, and Europe has had a very structured program over many years, increasing year by year the number of fuel cell buses. And now they're really starting to take off with all the experience, and those numbers are growing rapidly. And we're also seeing in the US, they're a bit later to come to this, but they're starting to really grow now as well. So looking at the trucks, I mentioned I wouldn't want to go into buses and trucks. Commercial trucks or freight trucks are an area that we really need fuel cells for. It's very difficult to power those with batteries. So if we look at diesel truck, and they have good range, they have good capacity for payload, they can refuel in 5 minutes. So that's the ideal. That's what we're used to. That's what all the economics are designed around. If we go to a battery truck, then we see that a lot of that payload that the truck carries is taken up by the batteries. So the weight and size of the batteries will significantly influence or impact how much the truck can carry. The range is much shorter, and it needs 3 to 5 hours to recharge. So this has a significant impact to the trucking companies and to distribution of goods. If we now combine the fuel cell with the battery, and now the fuel cell is charging the battery en route, you don't have to stop to charge your battery anymore. You just need to refuel your tank with hydrogen. Then we can get almost the same range. We have very little impact on our payload, and the refueling is within 15 minutes. So currently, the fuel cell trucks can haul a similar payload, and we expect future fuel cell truck weight reductions through lower weight hydrogen storage tanks and improved integration to improve that further. So trucks powered by Ballard, we're working with a number of different companies and applications. There are over 2,200 urban delivery trucks in service in China with Ballard fuel cells. We're working with Kenworth on a classic demonstration truck at the Port of Long Beach. There are United Parcel Service Class 7 trucks in California. There's a very large 60-ton truck demonstration project in Alberta here in Canada. That's a double trailer truck. Also, there's refuse trucks in Europe and mining trucks in China and South Africa. So getting now into the technology a bit more. So we continuously invest in our technology and our product development. And looking at the fuel cell, the fuel cell consists at its core where the proton exchange membrane, we've seen some pictures of this. On either side of that proton exchange membrane are the catalyst layers. And then the gas diffusion layers, which is a carbon paper. This is a very thin sandwich called the membrane electrode assembly, and that's encased with plates, conductive plates and seals, and that's our unit cell. And that's where the power is produced. And those are stacked together in multiple units to create a fuel cell stack. Those are combined with balance of plant components such as air and fuel handling. And that's the fuel cell module that then we sell to our customers for integration into the vehicles. So now looking a little bit more at the membrane electrode assembly. That's again the proton exchange membrane, the anode catalyst and the cathode catalyst. These are the electrodes. And the cathode catalyst is where most of the catalyst is in the cathode layer, and very high cost. So if we look at the fuel cell stack cost breakdown at high volumes, we see the catalyst accounts for up to 41% of the stack cost. So that's very significant. Clearly, if we want to reduce cost of fuel cell, that's an area to focus on. So just going a little bit more into the catalyst layer design. So we've seen some very good pictures of catalysts, what they actually look like. This is schematically, we either have platinum or a platinum alloy. It can be alloyed with things like cobalt, niobium, for example. Those very small particles of 3 to 6 nanometers are supported on a porous carbon particle of about 50 nanometers. Those catalysts have to have very high activity towards oxygen reduction to convert the oxygen to energy. They have to have low degradation rates. We've seen some information on that already due to voltage cycling or carbon corrosion. Those particles are then combined in a layer and put on top of the membrane with some of the same material as in the membrane, the ionomer, and that has to transport protons. So overall, the catalyst layer needs to have good proton conduction pathways, have good pathways for oxygen to access the catalyst, and be able to remove the water that's produced and be durable. So in terms of the approach to reduce catalyst, we look at many different factors and we design the overall stack and the overall application. We look at the current density it's operating at, how much catalyst you use, how you operate it, because that can significantly impact your degradation and your performance, how much performance you have at the beginning of life, how well you utilize the catalyst you have to have the highest utilization you can, and how robust it is. And in parallel to doing that with optimizing current catalysts, we continuously look at the advanced catalyst. And we're very interested in catalysts such as what Ballard just showed around the powder catalyst. Some advanced catalysts, we continuously evaluate and look for ways to introduce those. So what happens if you have a more active catalyst? Then you can have more better performance in your fuel cell. So we characterize fuel cell performance by the amount of voltage you get per given current. And by having a more active catalyst, you can raise that voltage, which translates to an increase in performance or increase in power produced. So if you have more power produced, you can have less cells, or you can reduce the amount of catalyst you have per cell. In either way, you have a cost reduction. And of course, the durability is very important. So we see that catalysts can impact the durability. This is a test run in the lab with a fuel cell stack under simulated operating conditions. Ballard mentioned voltage or accelerated stress tests. I'm not showing those, but I'm showing a durability test that runs in the lab. And here it is at the beginning of life. This orange curve shows a high-performing catalyst, higher performing than this other catalyst. But you can see that the blue represented catalyst is more durable. So over lifetime, the more durable catalyst is the better choice. But we always have to optimize that depending on conditions and requirements. So our next steps overall for the industry and technology is to continue to support demonstration and pilot deployments, foster collaborations across the hydrogen ecosystem. We're always interested in collaborating. continue to invest in development of fuel cell technology and products, drive cost reduction to meet market targets, develop industrial partnerships, and reduce the carbon footprint of our products and our operations. And I'd like to thank you for your attention, and I'll turn it back to Sophie.